This is EDEXCEL GCE Physics A2 level, Unit 4, Physics on the Move from June 2011, and we're doing the multiple choice questions. Question 1. A body is falling freely under gravity. The rate at which the body's momentum is changing is equal to its and one of these things. Well, if you remember from Newton's laws, he said that force was equal to the rate of change of momentum. Okay, change of momentum over time is force, and the force on a freely falling object is its weight. Okay, question 2 then. A circular loop of thin wire is placed so that its plane is perpendicular to a magnetic field. As the switch is closed, the loop of wire will do one of these things. And we need to recognize that because we've got a plus here, the current will be coming up on the front side here and back down on the reverse side. So we need to do a left-hand rule on this and figure out what way the force on the current carrying conductor will be. And if you left-hand rule this, you've got field pointing to the right, you've got current on the front pointing up, and when I do that, I'm getting a force that's that way for this side. If I do the same thing on the other side, again, field pointing to the right, and on the back end we've got current pointing down, and I'm getting a force that's inward at that case, so inward there. So that's going to follow round. If you follow, keep your first finger pointing to the right and follow current round, all the forces on the loop are inward, and that means that the answer is that it will shrink in a little bit. Question 3. The unit of time constant for a resistor capacitor circuit is one of these. Okay, so the time constant of something is RC, but it's more fundamental than that. The time constant is a time for a certain thing to happen. So it can have units of resistance times capacitance. So we could look at T equal to RC and say that this will be in seconds or in ohms times like farads. And so it's actually this one that we're looking for. Question 4 then. The diagram represents two coils. Coil X has 1,000 turns and a cross-sectional area of 10 centimeters squared. It's carrying a current which produces a magnetic flux density of 0.02 Tesla. Coil Y has 50 turns and a cross-sectional area of 4 centimeters squared. The flux linkage with coil Y is how much? Okay, the important thing here is that one coil produces a B value there. So the other details of it are not really important. It's coil Y that's going to be picking this up with its N value here and its A value here and B. Okay, so the linkage is just N, B, A. Okay, now we have to be a little bit careful because we've got a dodgy unit here. But we need to do a calculation with our 50 turns times our 0.02, oh I've got that wrong, sorry, 0.02 times our area, which is 4 over like 10,000 in meters squared. And I'm getting 4 times 10 to the minus 5 of a Weber for that. So we can see that there is an option of that value, and it's C. Question 5. A car, mass M, drives over a circular humpback bridge of radius R with a constant speed V. When is at the top of the bridge, the force on the car from the bridge is given by one of these things. So we assume that the bridge provides some kind of normal reaction on the car. The car itself has a weight mg, and what we need is for the force towards the centre of the circle to equal mv squared over r. And so the force towards the centre of the circle is going to be like mg minus r. Okay, I'm just writing the downward force as mg minus r, and we need that to be equal to mv squared over r. What we now need to do is get r on its own, and so we add r to both sides and subtract mv squared over r from both sides. So we get that r is over here then, and we get mg minus mv squared over r, and so it is this one. So D is the answer there. Question 6. The diagram represents two identical coils X and Y. The planes of both coils are parallel and their centers lie on a common axis. Coil Y is connected to a cell, a variable resistor and a closed switch. Under which of the following circumstances would a current be induced in coil X in the same direction as the current shown in coil Y? So we need to think about the circumstances here that they're asking us to look at. What will give us the behavior that the current in this one will be in the same direction? That's all they're interested in as the one in coil Y. Well, firstly, if we right hand grip the front of coil Y, we find that the fingers of our right hand are coming in and going out like that. So that's the direction of the field. So under what circumstances would we get the same field here? So if this is like the south, this is the north, this is going to be the south, and this is going to be the north. So under which circumstances do we get essentially attraction between these two coils? Well, we can rule out A, because if you move them closer together, the coil X will, from Lenz's law, produce opposing poles. So it'll produce a north nearest Y. So that can't be what happens in A. The switch is opened. Okay, if we open the switch, the field here will collapse in the first coil. The field will collapse. That will cause a reduction of a north pole. And that should then cause something like this as the field decreases. The resistance of the variable resistor is decreased. That's very similar to A, where you're increasing the field approaching X. So that can be ruled out. And no change is made. Well, there's not going to be anything happening in X if no change is made. And so it's opening the switch. Opening the switch causes the field here to decrease. That's equivalent to bringing, if you imagine this was a magnet, bringing it away will cause an attraction. Lenz's law says that the behavior of X will be such that it opposes the change. So if we reduce the field here, that's like bringing a magnet away. And if we're bringing a north pole away, the south will appear here to attract it back and thus oppose the change causing it. So it's going to be B. Question 7 then, a proton is moving in a circle of radius 1.5 meters within a magnetic field of flux density 0.02 Tesla. The speed of the proton must be this. It's just straight calculation work. The force on a charged particle moving in a magnetic field is BQV. And that has to be equal to that required for circular motion, which is mv squared over r. Sorry, my v's and my r's are looking similar there. That didn't help. So we have this expression for what goes on with the behavior of the proton. We do know all these properties. We do know R, we do know Q and B. We can get those, we can get Q from the data sheet. So we just need an expression for V on its own. So we just rearrange this to get V on its own. So V would equal BQR over M. Just rearranging that. And then we need to fill that in and do a calculation using those values. M is the mass of the proton here. R is the radius they've given us, B is the value they've given us, and Q is the charge on a proton, which is the same as the charge on an electron. So we've got 0.02 times 1.6 times 10 to the minus 19 times 1.5, all divided by the mass of a proton, which is like 1.67 times 10 to the minus 27. And then we fire all those into the calculator. And I'm getting a value for V equal to 2874251 meters per second. And there's only one value there that's anywhere near that. You could look at this in other terms. You could look at this as let's not even bother doing a calculation. This is ridiculous. It's bigger than the speed of light. So's this. This is ridiculously small. So even if you hadn't a clue what to do here, you could still get that answer. Question 8. A positron is found to have a mass of 1.8 times 10 to the minus 29 kilograms. It can be concluded that this positron is A, a proton, B, travelling close to the speed of light, C, travelling at non-relativistic speed, D, travelling in a circle. So we're looking at the idea that the mass of this, since it's a particle, sort of the electron's evil twin, it should have the mass of an electron. So the mass of an electron, remember, is like 9.1 times 10 to the minus 31 kilograms. Now this is clearly more than that. So the only reason this particle could have more mass than it should do is if it's travelling close to the speed of light. Okay, so non-relativistic speed, no, because it should have the right mass then. Travelling in a circle is irrelevant. Proton, we've just already said that it's a positron, okay, and it's the wrong mass for a proton anyway. So travelling close to the speed of light is the answer. It's relativistic effect that we're noticing here. Question 9. The mass in MeV over c squared of a 1.8 times 10 to the minus 29 kilogram positron is one of these values. So this relates to the previous question where we had a positron of that value. So the MeVs over c squared for this is basically converting that mass into units of MeV over c squared. Kilograms are like joules over c squared, so we're really converting it to MeVs over c squared instead. So we need to do a energy conversion on that and figure out how much it is. So we need to find the energy belonging to 1.8 times 10 to the minus 29 kilograms. So the energy is going to be the 1.8 times 10 to the minus 29, and then we multiply by c squared. That will give us an amount of joules. And if we divide that by the electron charge, that will give us it in eV. And that's giving me a value of 101.25000. EVs, which is 10.125 MeVs, which means the mass will be that value over c squared. So it's A. Question 10. The Large Hadron Collider is designed to accelerate protons to very high energies for particle physics experiments. Very high energies are required to do one of these things: annihilate hadrons, collide hadrons, create particles with large mass, produce individual quarks. Well, the energies are all about making available large amounts of energy to be converted into mass, so the answer is C. And that's it.